For that purpose, nature has provided them with tough antlers, made of bone. Despite energetic wrestling, broken antlers are very rare. But bone is heavy, so nature is as economical as possible. Inside, bones are partly hollow, but filled with a complex network of arches and spans. This beautiful hidden structure is also elegant engineering. The bony struts are laid down along lines of stress in the bone, so it's strongest where it feels the biggest loads. It's as strong as it can be, but using the minimum of material. Even our own skeletons can be a source of inspiration. The human thigh bone, or femur, is especially elegant. The head of the bone is off to one side, which means the weight of the body has to be transferred, first sideways, then down the length of the bone. Struts of bone arch through the head of the femur, transferring this weight both effectively and economically. And architects realized they could apply exactly these principles in constructing tall buildings. It's the inspiration behind one of the most famous buildings in the world, the Eiffel Tower. Gustav Eiffel used the structure of the human thigh bone in building his 300-meter tower, the tallest building in the world until 1930. Like the curve in the head of the femur, the famous iron curves of the Eiffel Tower are supported by a latticework of metal struts and girders that transfer the tower's weight sideways and down to the ground, just as elegantly as the internal struts of bone. In recent years, more and more designers and engineers are looking at the way nature builds bodies and getting inspiration for everything from new bridges and buildings to cars. Cars need to be tough, but can't be too heavy or they burn too much fuel. Nature faces the same problem, which is why both animals and plants only lay down material precisely where they need it. So this car-shaped fish, the boxfish, might be a good model for an economic car. And when the engineers at Daimler Chrysler designed a chassis using a computer program that, like the boxfish, laid down more material where the loads were greatest, they found they'd made their lightest, strongest chassis ever. For vertebrates, like fish, mammals and birds, the skeleton gets its strength from the material of bone and the way it's constructed. Vertebrates are built around the outside of these internal bony struts, a system that works well for the biggest animals, like these moas, giant extinct birds. But there are other types of skeleton. Insects are the other way round. Their skeleton is on the outside, an exoskeleton. An insect is hung from the inside of a tough protective casing, the optimum engineering solution for small creatures. Bones are strengthened with deposits of heavy calcium phosphate, but tiny insects can't afford so much weight. Natural selection has had to come up with a lightweight solution, a structure made of fibers of a substance called chitin, embedded in a matrix. Like plywood, each layer of fibers runs at a slightly different angle, making the exoskeleton very strong in every direction. Tough enough for male stag beetles to use their jaws like the antlers of an elk, wrestling with each other over females. Other insects use their jaws for their original purpose, for eating. Locusts eat grass, lots of grass. Grass leaves are protected by tiny crystals of silica which wear away most substances. But the jaws of a locust can cope. And before they're in danger of wearing out, a young locust can replace them by shedding its whole outer casing. Insect cuticle is remarkable stuff. So what can we do with it? First, we need more than we can get from tiny insects. But on the east coast of North America, a huge supply of chitin crawls out of the water onto the beach every spring. Horseshoe crabs are not insects, but neither are they crabs. They're primitive creatures related to spiders that have swarmed onto beaches to spawn like this for hundreds of millions of years. But like insects, their shells are strengthened with chitin fibers. They were collected for their shells, but over-collecting has reduced their population. Not a good way to work hand in hand with nature. Fortunately, the eastern seaboard of the United States offers up another chitin bounty. And most of this is going to be thrown away. A much better source. Crab factories around North America's Chesapeake Bay extract the valuable meat for canning, but the shells themselves could be just as valuable. The shells of crabs also contain lots of chitin, but it's bound up with calcium carbonate. However, by treating the shells with acid, this can be dissolved, releasing the chitin for use. By purifying the chitin and chemically altering the fibers, a substance called Keitus can be made. In its purest form, it's used to make contact lenses, skin creams, and wound dressings. But Keitus can also fill many of the purposes of plastic. And even better than plastic, it's biodegradable. But smashing up this amazing substance and converting it into a bioplastic may not be the best way of exploiting its potential. An insect's exoskeleton is a marvel of microengineering and almost endlessly versatile. It can be shaped to resemble a leaf with amazing accuracy, living or dead. Even down to the holes chewed by other insects. The level of detail is extraordinary. Hidden in this orchid flower is an orchid mantis. Its body and legs are sculpted and colored to match the petals of the flower exactly. It's virtually invisible to its predators and to its prey. But look even closer, and the insect's body armor is even more astounding. Molded and shaped with microscopic precision into a huge variety of shapes. And it's not just there to admire. Each of these microscopic landscapes has a job to do. These tiny bumps cover the body of a beetle that lives in the Namib Desert. In this parched desert, it hardly ever rains, yet beetles seem to flourish here. Their only supply of water is the fog that rolls in from the ocean every morning. So the beetles start each day by climbing to the top of a dune, where they can intercept the fog blowing in on the wind. Those microscopic bumps help water condense on their bodies. The tips of the bumps attract water, while the channels between repel it. This forces the water to form droplets which run down to the beetle's mouth. A desert survival strategy that might help with all too frequent water crises in the human world. One company is now designing tents for refugees that work in the same way. These tents could condense water from the air each morning, even in areas where groundwater is in short supply. In this case, understanding how a desert beetle lives could make all the difference between life and death for these people. And all this comes from the extraordinary design of insect skeletons. Yet this whole complex structure is shed and replaced every time the insect molts, which seems something of a waste. Insects can afford to do this because the arrangement of chitin fibers is self-assembled. When the right components come together in the right way, the exoskeleton just builds itself. And this kind of self-assembly process is very interesting to biomimetic engineers. Crystals are a simple example of self-assembling structures. The final shape of a crystal is not due to some elegant overall design. It happens because the atoms or molecules naturally come together in a lattice that, as it grows, results in these familiar shapes. More complex molecules can self-assemble into more complex shapes. If we could control the way the component parts of a material interact, we could just mix them together, sit back, and watch the most complex of designer materials just build themselves. Impossible? Nature does it all the time. One impressive example can be seen off the coast of California. Here, sea otters seem to live an idyllic life, floating on a gently rolling ocean. And when they're hungry, all they need to do is dive down to the ocean floor and pick up a tasty shellfish. But it's not that easy. Shellfish have tough shells, so tough that sea otters have to resort to a clever trick. They hammer the clam on a stone balanced on their chests, and eventually they'll get their reward. As smart as the sea otter's trick looks, it's the discarded shells that are really interesting. Why